Okay, so in this video, I'm going to give you a numerical example. I'll think about a drug dosage. So, say FDA wants to test if a medical drug has a correct dosage. So here, just for simplicity, I'll think about Bayer aspirin. The lowest dosage is like 81 milligram. So, of course, like if the manufacturing process is correct, the dosage should be 81 milligram, should be correct. So we will test it. Of course, it's not real data, just hypothetical numerical example. So what we want to test here is this null hypothesis. We believe that the expected dosage of a randomly chosen tablet is exactly 81 milligram. Okay, mu is the true mean of a tablet's dosage. But the alternative is anything else. If it's different from 81, then the drug is has a problem, right? Okay, then let's think about, like we learned the critical value approach in the previous slide, right? So suppose that you random sample 100 tablets of aspirin, right? And measure their dosage, right? But suppose that measurement errors are common, like prevail, like so, it can occur with a standard deviation of 5. Suppose that the standard deviation is known for now, for simplicity, and you can imagine that this measurement error depends on the scale you are using. So the scale has a standard deviation of 5, right? And then in this case, without any data, you just plan to sample 100 tablets. Can you calculate the critical values for the significance level of 5%? We did this in the previous chapter, so think about it. I think do the algebra should be simple enough. The formula can be found in the previous slide. Okay, so first, you don't need to look at the data to calculate the critical values. That's the advantage of using the critical values. Critical value does not require data except for the standard deviation. In this case, I suggested a special, the standard deviation that is attached to the scale, not the data, not the tablets. So anyhow, X bar is not necessary to calculate the critical values, right? And then you remember the critical values are calculated centered around your hypothesis, which is 81 milligram, and you add plus minus the margin. The margin is based on Z alpha over 2, which depends on the significance level, 5%. So then 5% significance implies 1.96, right? 1.96 is plugged in here. And standard deviation 5, sample size 100. So you calculate them, then you get critical values. Okay? So this is the power of critical values. We are going to, in this chapter, in this part, we are going to use critical values because when we calculate type 1 error, type 2 errors, error probabilities, we are thinking about the randomness in the sample average, right? So, like, before looking at the data, before making the decision, we know how many times we are going to make the errors, depending on the random errors, okay? So, in this situation, in this context, critical values are really useful because same critical values can be applied to different realizations, different data. So we are just using the same critical values. But if you used p-value or t-statistics approach, you have to recalculate those p-value and t-statistic every time you get a new data. So there will be more algebra, less convenient in calculating the error probability. So we are going to use the critical value approach to calculate type 1, type 2 error probabilities. So you will see why it's convenient in the coming slides. Okay, let's first think about the type 1 error probability. So remember, type 1 error happens when you reject the null hypothesis, but it is actually true. So you should have not rejected the null hypothesis, but you rejected it. Of course, when you reject it, you don't know if it's true or not. But in our analysis, so, our assumption is that the null hypothesis is true. So first, that fixes the mean. The true mean is 81. Your hypothesis is true. But you had to reject it. You rejected it because the realized sample average is less than the lower critical value or greater than upper critical value. So it's outside of the critical values, but those critical values were calculated here, right? So it's if the realized sample average is below 80.02 or greater than 81.98, then you have to reject the null hypothesis. Something is not correct. Okay. Therefore, our type 1 error probability can be calculated like this, right? So, and under the condition that the true mean is 81, this is what we are going to calculate, right? So your type 1 error probability is the rejection probability, but rejection happens when this happens. Like it's actually tail probability. The tail probability outside critical values. Then how do we calculate that probabilities? You know how. Because we are going to approximate x bar, like the sample average, to a normal distribution, and we know their parameters because the mean is 81, because that's our assumption. We assume that the hypothesis is true, so the null hypothesis is true, so the true mean should be 81. And the standard deviation was assumed to be 5, and sample size was 100. So this is also known. So you know the parameters for the distribution of sample average. Okay? Now, using those parameters, you need to calculate those probabilities by standardizing the probabilities. So x bar smaller than 80.02 will be standardized to z smaller than 80.02 minus the true mean, 81, divided by standard error, 0.5. Okay, so if you do the math here, it's minus 1.96. So the left-hand side, the probability that you have to reject the null hypothesis because the sample average is too small, that probability is smaller than minus 1.96 on the standard normal distribution. You can calculate this from a calculator or Excel, right? You can do the same thing on the other side, tail. The other side tail has greater than 81.98. Then after standardization, you get greater than 1.96. Okay? So it's like symmetric tail probability, so they must be the same. And according to the calculator, if you use Excel, you will get 5%, right? That is type 1 error probability. Okay? One thing I'd like to mention here is that I did not give you the data at all. Like x bar is never used. We don't need to look at the realized value of x bar at all, right? It's only about the sampling distribution, the parameters, right? Because once x bar is realized, there is no more randomness. X bar, if you observe an x bar, it's always rejection or not. So there is no probability. So that's this is the main difference when we calculate error probabilities. Okay. And one more thing. So, you may think, oh, these numbers are familiar, right? plus minus 1.96 and 5%. They are actually uh, this like 5% is from here, 1.96 is from here. Okay, why do we get those numbers again? Because when you calculate the critical values, you have used this formula, right? And when you standardize the probability, you actually do the reverse transformation, right? Critical values are calculated like this, but you standardize the critical values, right? Remember, critical value is 80.02. Oh, that is standardized again, but the standardization subtract mean cancels out this part and divide by the standard error cancels out this part. So it returns you the z alpha over 2 again. Okay, and z alpha over 2 is the value that gives you alpha over 2 on each side tail probability, right? So by construction, it must be the same z alpha over 2 and the same alpha significance level in the end. So as a result, you did not need to do the algebra at all. Type 1 error probability is always the significance level, always. Okay. So this is like you can think it this way. H0 is the null hypothesis is rejected when the p-value is smaller than alpha, right? That's how we started our p-value approach. That means the higher alpha is, the more rejections. When you increase alpha, you are rejecting more. So when you reject more, so type 1 error happens only when you make rejections. So when you are willing to make more rejections, you are going to make more type 1 errors, right? So as a result, actually alpha is type 1 error probability. Also, you may understand it like this. Like in the previous chapter, I explained alpha as the percentage you are willing to reject, right? So there are innocent people, even though you assume that everyone is innocent, you have to reject some of them who are really suspicious, right? They are exactly type 1 error, right? They are innocent, but you have to reject them. That is alpha. How many you are willing to reject? It could be 5%, like 10%, 1%. So that is again type 1 error probability. So some textbooks start with alpha as a type 1 error probability, right? In the end, so they are the same. Anyhow, like whenever I ask you the type 1 error probability, you just look for the significance level. They are the same thing, literally, okay? No algebra is needed. Okay, then now, so type 1 error probability is actually pretty simple. The conclusion is you did not need to do this math at all, just it is significance level, okay? But type 2 error probability is actually more involved. Like type 2 error happens when you do not reject the null hypothesis, even though it is wrong. Type 2, if the null hypothesis is wrong, you have to reject it. But if you fail to do that, that is type 2 error. Okay. Then in our setup, the null hypothesis is not rejected when the sample average is in between two critical values. Okay. So that is simple. That is clear. We are thinking about non-rejections. That happens when these inequalities hold. But the problem is, how can we specify the wrong null hypothesis? So when I say the null hypothesis is wrong, that means the truth can be any value different from 81, right? So the alternative is defined by like negation of equality, which does not give you any specific number. So we have to choose on like an arbitrary number, like to do the math, to do the algebra. In here, I will consider 82. So it could be 83 or it could be 80, but as a numerical example, I will show you 82. But you can use any other number other than except for 81. So whatever number you use, you can calculate type 2 error corresponding to the truth. Okay, then under this setup, we are going to calculate the probability of type 2 error, which is the probability that you do not reject. So X bar, the sample average, is within the acceptance region under the condition that the true mean is 82, right? This is our assumption, right? And then again, we are going to use the central limit theorem to approximate the sampling distribution to a normal distribution. But in this case, the variance is the same, but the center is now 82, right? Because the null hypothesis is wrong, and we assume that the 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 distribution is generated from 82. This affects your standardization, right? So we are calculating this probability, and you know you have to standardize X bar, but when you standardize, you have to use the parameters like this. 82 appears here and here, so you get different numbers. It's not plus minus 1.96, right? That's because when you calculate the critical values, you assumed the null hypothesis is true at the time when you calculate the critical values. But now you are assuming that the null hypothesis is wrong. So we are assuming a different true mean. So as a result, it's not symmetric. It's not exactly cancel out the mean. So you have a non-standard probability, which again you have to use calculator or normal calculator or Excel. Okay, so then you will get 48.401% from Excel. Okay, so then what you can learn from here is that, so as you can see, if you chose say 83, 84, then the probability will be different because those numbers would be different. Okay, so type 2 error probability depends on the value, right? So like you can understand it like this. I'm testing a aspirin is 81 milligram or not. If it is 82 milligrams, then it is wrong sized, but the difference is only 1 milligram. So it's really hard to tell. But if your aspirin was like say 100 milligram, which is much more wrong than before, and then it is actually pretty easy to tell this is wrong. So whether you can make a correct decision or not, correct rejection or not, depends on how wrong your hypothesis is, right? So the smaller difference, the smaller deviation from the truth, then the more difficult to detect the difference. That's the key idea, right? In this case, I only assume 1 milligram difference, which is very difficult to detect. So 84%, you will fail to detect that difference, whether it is 82 milligram or 81 milligram, or the difference is just measurement error or not. That's different. And also, type 2 error probability depends on alpha, but it's not clear. But intuitively, you can explain that. So type 2 error happens only when you do not reject, right? So type 2 error by definition is non-rejection of wrong hypothesis. So if you reject, then type 2 error is not a concern. But when you don't reject, it could be type 2 error, right? So if you are rejecting more, if you are willing to reject more by choosing a higher significance level, then you are going to reject more, so there will be fewer type 2 errors. Because when you reject, type 2 error does not happen. So higher alpha means fewer type 2 errors. So that's also kind of intuitive trade-off, like not trade-off. So yeah, trade-off because alpha is type 1 error. Okay, so type 1 error and type 2 errors are trade-off. The more reject, if you are willing to reject more, then you will make more type 1 errors but fewer type 2 errors. So we have to think about how to balance them out. In general, the philosophy is that type 1 errors are more serious problem than type 2 errors. That's just underlying philosophy. Because that's why we favor the null hypothesis than the alternative hypothesis. It's like presumption of innocence. We would like to assume that everyone is innocent. So that's why we put type 1 error probably under our control by choosing alpha. So we control type 1 error probability, not type 2 error probability. Because type 1 error probability is more serious problem. We set our willingness to make type 1 error probability. So this in law there is a it's a principle by Sir William Blackstone. I don't know who he is. He's a 18th century judge and politician who said it is better that 10 guilty persons escape than that one innocent suffer. Like exactly this is the underlying philosophy behind hypothesis testing. We are not willing to reject a true null hypothesis. If it's true, we try to avoid rejecting that. But the other way is not as serious. Like we may not reject wrong null hypothesis. That's okay, but we are going to maintain the null hypothesis as much as we can. Okay, this is the how we calculate type 1 and type 2 error probabilities. Also, remember that I did not tell you any specific value, any realized value of the sample average. Like X bar is not realized at all. Still, you can calculate error probabilities because error probability does not depend on just one decision. It's if you make one decision, there is no more randomness. Okay, thank you for watching. In the next video, I will continue similar example with a different dosage. Okay, see you later.